Well, hello, Nick here, M0NTV, and welcome back to my shack and to another video. And it's a bit like buses, isn't it? You know, you wait for ages, you don't get anything, and then two come along at once. So this one has come fairly quickly on the heels of the last one, because I've been building some stuff recently, so I thought I might as well document it as I'm doing it. It's also related to the last one about the bandpass filter, because I'm afraid, yes, it is another filter, and I promise after this one I'm not going to do any more videos about filters for a little while, right? Because I'm just filtered out. I'm sure you are as well. But this one is really important, and if you're ever going to do any kind of building of a superhet receiver or a transceiver, then you're probably going to have to get to grips with this, because this is the Crystal Ladder filter. And if you thought that bandpass filters were a dark art, well, you ain't seen nothing yet. And that's why I call it crystal filters for the fearful, because I'm going to show you another way, a different way, a simpler way to actually build a crystal ladder filter. And it's not original to me. You know, I've learnt it from various other people on the internet, chiefly Charlie Morris, ZL2CTM. He's done some brilliant videos on his designing and building of this particular kind of crystal ladder filter. And I'll tell you a bit about that in just a moment. But why would you want to do this? Well, probably because they're kind of hard to get hold of now. I mean, you used to be able to pick up commercially made crystal filters, and you still can, you know, the kind of thing that, you know, radio rallies were awash with them, but most of them are wide as a barn door. They're intended they come out of FM radios. So for SSB, they're just not a lot of use. And places like the GQRP Club, the club sales, Graham used to have a load of them that he was selling, but they're all gone. They're long gone. So actually, it's kind of hard to get hold of these things, which is what drove me to actually start kind of homebrewing my own. And it's don't be fearful. It's not as terrifying as it sounds. And so you're going to see, hopefully, a simpler way and a way of getting into this. I'm not going to pretend that the filter that I built, you know, is going to compete with the best of the commercially available ones. But it's good enough, right? It's good enough, and it's a great way of starting to dip your toe in the waters of crystal filters. Now, apologies, this video runs a bit longer really than I wanted it to, but I'm covering quite a lot of ground, so we're going to tackle it right from the beginning of selecting your crystals, how you measure them and sort them out, and the equipment that I use to do that. We're going to look at the actual schematic, the design that we're going to follow. We'll look at the build of it, and then really important, we're going to look at how you impedance match that filter, and finally testing it. So there's quite a lot wedged in here. So if it's too much for for one sitting, split it up. Come back to it. Anyway, hope you enjoy. Right. So our crystal ladder filter starts with a big bag. I think I bought 100 of these crystals from AliExpress, and I think you should just be able to see there. They're rated at 40 megahertz, but I should have done my homework and researched this a bit better, because when I put them on the frequency counter, they're not 40 megahertz at all. They're 13.3 megahertz, because they're designed, they're what they're called third overtone crystals. So in other words, they're crystals that are designed to be used at their third harmonic, which is 40 megahertz. But for building a crystal filter,
that's not all that useful. So I'm actually going to use them, or try and use them at least, at their resonant frequency, which is 13.3 megahertz. So the first thing you have to do is, of course, measure them. So how do you do this? Well, how I do it, if I come over here, is with this gear here. So what I've got here is, first of all, a little frequency counter. Again, I think I got this from Banggood or AliExpress or something like that. This is useful because, well, technically it's accurate to within 1 hertz. Now, whether it actually is accurate to within 1 hertz, I would doubt very much. But it's reasonably accurate. I mean, I've tested it with my signal generator and other things, so it's pretty accurate. But the main thing is that doesn't matter all that much. What we want is consistency when we're measuring crystals. So that's going to give me my readout, and that just it runs on 12 volts. There's a voltage regulator on the back of it. Actually, I think it actually runs on 5, I think, but the 12 volts is fine. It'll go through the regulator. And that is coming, being fed by a, I always never remember his call sign, G3UUR. This is the classic design. It's a little oscillator, and you can just see there, those 3 little pins. The 2 outer pins, you insert the crystal in there. I'll show you in a moment. Now there's a switch here because you can switch capacitance, a certain fixed amount of capacitance in, I think it's about 30 picofarads from memory, in and out. And that's intended for measuring the motional parameters of the crystals. To be honest, the filter I'm building is a cone filter. It's a minimum loss filter, and actually it's a lot simpler than that. So I'm not even going to bother with all that. All I want to do is to group the crystals according to their frequency as accurately as I can. So let me just grab one here, and I'll try and show you. Do this with one hand. So it goes in here. I can do that on one hand. And if we come over to the frequency counter, okay, so now you can see that there's a bit of fluctuation there. But initially, I'm just going to group them down to an accuracy of 1 kilohertz. So that would be 13.325. Okay, so 325. So I'll pull that off here. Now, if I come over here, hopefully you can see this big sheet of paper here. Now, you'll also see where the center frequency is for these. 325. I've got a great big long. Now, that's another 325 there. And what I will do, and as you can see, 324, 325, we've got an awful lot of them, which is great. What I will probably do for both of those, once I've tested the rest of them, I haven't got many more to go, is to go back, say, through the 325s and group them again, but this time down to a higher level of accuracy. So initially 100 hertz, and if I can, maybe even down to 10 hertz, but that might be pushing it a bit. But for an SSB filter, if I could get them down to within 100 hertz, then that would be okay for the kind of filter that I'm building. Right, okay, so I've finished going through all the crystals, and what I've done is I put them in their kilohertz groups into some envelopes so I can go back and use them again. I only had 5 dud ones that were dead. In fact, no, I think I only had 4 actually dead ones, which is pretty good at a batch of 100. Now I selected the 324s, and I had 28 of those. And what I've done is I've gone through the 324s again, this time to the next decimal place. So this is to within 100 hertz. So this is essentially 13.3240123, etc. And you'll see that I've got a few groupings of 4 to within 100 hertz. So if I wanted to use a 4-pole filter, that would be okay. But what I might try, just because I've got a few of them, is if I can get any lower down, higher accuracy with the ones. So if I can maybe get down to the with maybe 50 hertz or something, I'll have a look and see. Got nothing to lose, and I'll give it a go. And finally, from 100 down to 4, and I've managed to get the those that were there, the 13.324 ones. I'd look at those, and really any of these would be all right. But yeah, I managed to get 4 that are within, between 20 and 30 hertz of one another, which is ideal for an SSB filter. So that should suit me very well.
Okay, so we've got our crystals. Now all we need to do is build the filter. So, and to do that, we need a schematic. So here is the schematic which I used, and this is what's known as a cone filter, a minimum loss filter. And you can find this design in various places on the internet. I think I probably got it from Charlie Morris, ZL2 CTM, who's done some great work and some brilliant videos on his efforts to homebrew Crystal Ladder filters. Now, the thing to notice, don't worry about the transformers. We'll come back to those in a moment. But just to notice, it is a very simple design. There is a series capacitor here into the first crystal, and there's a series capacitor here into the final crystal. And then the other capacitors are shunted to ground in between. Now, you'll notice that each of the capacitors is the same value. And that's the thing about a cone filter, which greatly simplifies the design, and the construction of it as well. And as a matter of fact, the amount of capacitance will affect the bandwidth of your filter. The greater the capacitance, the narrower the filter will be. And there's an awful lot of experimentation with this, which is kind of what ham radio is all about. Now, I built a few of these actually for a higher frequency, for 16 megahertz. And actually I found that I needed much more capacitance on this particular build for this 13.3 megahertz filter than I did for the 16 megahertz one. And I'm afraid the only way really is to just try it and see where you get. I mean, just to give you an idea, I tried a few different values of capacitors. So I started, I think, with 120 picofarads. Well, that gave me a bandwidth of 3.6 kilohertz. Well, obviously that's far too wide for SSB. 140 picofarads gave me 3.1, so it's going in the right direction. 150 gave me 2.9, so it's coming down. And then finally I went for 180, which gives me 2.6, so 2.6 kilohertz. So that's absolutely fine. Now I will show you what it actually looked like, and then we can come back to the transformers. So here is the finished filter, and as you can see, I've put it in my usual little metal tin, little Altoids-like tin, and I fitted a chassis mount BNC connector, both ends, and okay. So now here is what I've done. So let me see if I can get this a better angle on this.
And you can see. Right, okay, that's not too bad. So now you can see here instantly that the board bears the scars of several rounds of desoldering and resoldering capacitors. And as I said a moment ago, unfortunately, it's just part of the course. You have to do it, when you change the value of the capacitor, of course, you have to take them all off and put a new lot on, or you add capacitors in parallel if you're increasing the capacitance, which is what you're usually doing. So now these are actually NP0 capacitors, so they're the more expensive ones that don't change their capacitance very much at all, even when the temperature changes. So they're useful things to have. They are more expensive. I have made filters just using regular ones, but if you can use those, then obviously they're useful. I bought a whole load of these just for making filters, basically. Now, what else to point out? You'll notice I've bridged the cases of the crystals, and if I come around here, you can probably see it's actually grounded as well. And grounding the cases, it doesn't make a huge difference, but it makes a bit of a difference. So it's worth doing. You've got to be careful. You don't want to apply too much heat to those crystals, because you can cook them, and that's really going to spoil your filter. But so you do that, and so in the end, it's quite a simple thing. In various amounts of capacitance, I've had to have 2, even 3 capacitors at each junction to make up that parallel capacitance. But in the end, I went for 180 picofarads, and I happened to have some 180 picofarad capacitors, so that's what I used. Now you'll see there the transformers. These are impedance matching transformers. And what I actually did here, because the question is, well, how do you know what the impedance is? Very good question. This is another Charlie Morris ZL2 CTM trick, which is, you see you've got that series capacitor at the beginning and at the end. Well, what you do is you connect a little 200 ohm trim pot, which hangs off that capacitor and then goes to the BNC connector. And so you put one of those on either end, and then you connect the nano VNA to it, and then you adjust the trim pot till you get a nice flat pass band. Now the insertion loss will be atrocious because obviously you're dropping signal, your precious signal, over those trim pots. So you're not going to keep them in permanently, but it will just give you an indication of what will give you the flattest pass band. So the idea is when you've got it as good as you can, basically. So the insertion loss will be horrific, 15, 20, minus 15, 20 dB, something that's pretty unworkable. But it will look fantastic, so it'll be dead straight, hopefully. What you do is you desolder them, then you measure them, and hopefully they're not too far apart in their values. Then you add 50 to it, and then that becomes the notional impedance of your filter, and that enables you then to actually build some matching transformers, so that your filter will see the right amount of impedance, but also the stages connected either side of your filter will see 50 ohms. So we'll just pop back now to the schematic, and I'll show you what I did with that.
So here's our schematic again, and just have a little look at the transformer on the left, because they're both identical, but we're just going to look at the one on the left for a moment. So let's just clear off everything else, and that's it. So the measured resistance that I had, actually, when I measured those little variable resistors, little trim pots, was actually, believe it or not, about 50 ohms. So what you do is you add 50 to that. So the filter impedance is about 100 ohms, which actually is pretty much in the ballpark figure of what people who've built these say it is. It can be, 100 to 200 ohms typically. So 100 ohms, well, 100 ohms to 50, that's a 2-to-1 impedance ratio. So that's nice and simple. So how we calculate the turns ratio, the number of turns we're going to put on our toroid to match the impedance, is you take the square root of 100 divided by 50, which is the square root of 2, which is 1.414. So what we do then is we need to find a multiple of that number. We need to find a multiple of 1.414 that is as close as possible to a whole number. And the reason for that is that that figure that we arrive at will be another turn. It will be a number of turns on the toroid. So that's why it needs to be as close as possible to a whole number. And the only way to do this is to work it out. So here we go. So 1 times 1.414 equals 1.41 if we just drop it to 2 decimal places. 2 times is 2.83. That's not bad because that's almost 3. 3 times is 4.24. 4 is 5.66. But look at this. 5 times 1.414 is 7.07. So that's a good one. And in fact, that's the one that I used. So 5 times 1.414 is 7 if you drop the fractional part. And that's it. So 7 becomes the primary winding, and 5 becomes the secondary winding. And that will give you that right impedance transformation. So that becomes 7 turns to 5 turns. So obviously the 7 turns, which is the primary, is the 100 ohm end. That's the filter end, and the 5 turns is the 50 ohms end, and that's connected to your BNC and to whatever's going into your filter and out on the other side. And I used an FT3743 ferrite toroid. Now, there is another calculation that you're really supposed to do as well, which is just to make sure that you're going to get the right amount of impedance transformation that you think you're going to. I'll show you what that is now. So the other calculation that you're supposed to perform is a measure of the inductive reactance, and that classic home brewing Bible, solid state design for the radio amateur, suggests that the inductive reactance of your smallest winding really needs to be at least 4 to 5 times as big as the resistance that it's connected to at your lowest frequency of operation. Let me say that again. So the inductive reactance of the smallest winding needs to be 4 to 5 times the size of the resistance that's hanging off it, basically. Now you can calculate this. inductive reactance is 2 pi FL, 2 pi times the frequency times the inductance. Of course, you need to work out what the inductance is, so you can go to toroids.info, which you'll see here. But actually, if you just put one of the figure in here, it does it all for you, and I'll show you, and it's a lot easier. But you need to put the turns in anyway, because you've got to calculate the inductance. But actually, if you put the frequency in, so 13.3 megahertz, it'll actually do that calculation for you as well. And so the lowest, the smallest amount of turns, of course, in our case, is 5. So we put 5 turns in there, 13.3 there, hit calculate, and there you have it, 731 ohms. So we're well above the minimum amount that they suggest you have, and you'll see there's 8.75 microhenries of inductance on that smaller winding. So there it is. So yeah, and so it passes that test as well. Now I'm sure you just really want to know how well it works. So I've got it hooked up to the Nano VNA, and I'm going to try and show you. So now I've calibrated the Nano VNA already, and I've got a couple of settings. So I'm going to recall, first of all, number 4. There we go. So I was quite pleased with that in the end. You'll see there, that's the peak, that's the insertion loss, minus 2.28 dB. Very good, really, for a homebrew filter. You see, it's not as flat as it could be, but you know, I'll settle for that. It's not a huge variation. Now the other thing you can calculate, of course, is the 6 dB bandwidth, which is really important, because when you're actually going to use this as like an IF filter, you need to know where it's sitting. So essentially what you do is you get the peak, which is well, minus 2.3, let's say, and so the minus 6 dB bandwidth will be 6 dB below that. So you're looking at minus 8.3, thereabouts. So essentially what you do is you just go down till you get someone there. Okay, well, there we go, minus 8.23, that's probably close enough. So that's 13.323801. So you write that down, and then you go the other way. So you go to the minus 6 dB bandwidth and the other end. Oh, too far. You're not going to get it perfectly, probably. That'll have to do. Minus 8.6, so that's 13.326401. And so those become your minus 6 dB frequencies. That's where it's actually sat. So and if you subtract one from another, you get 2.6 kilohertz, which is your minus 6 dB bandwidth. But also you know where that frequency actually, where that filter sits now, what the frequency is. So when you're designing your radio, you can get your signal sitting appropriately through in that pass band. So there is, just to show you what it's like a bit closer up, we'll recall 3, I think it is. Yeah, so you can see it's not bad at all, really. Minus 3.2 there. The peak, minus 2.2, a bit lower down here. But, you know,
you've got no more than it drops off a little bit down this end, but essentially 1 to 2 dBs of ripple there. So yeah, so for just 4 crystals without any calculations of motional parameters put together, I think that's pretty good, really. And as I said, I've built them before, and seem to work pretty well in my homebrew rigs. So there you go.
Well, to the 3 people left watching this epic video, thank you. If you've got any comments or questions, by all means, stick them in the comments below. Clearly, I am in no way an expert in all this stuff. I'm like the rest of us, just a keen amateur. And but if I can give anybody any help or encouragement to give it a go, then that's brilliant. But until next time, look after yourselves. 73. Thanks for watching. Bye bye.